welcome back to the CH1601 video series. In this video, we are going to discuss the shapes and conformations of systems which are constrained to being cyclic. In particular, we will discuss 3 to 6 membered cyclic rings. So carbon atoms in these rings are all sp3 hybridized. This means they ideally want bond angles of 109.5 degrees. If we assume the ring systems to be planar, i.e. they lie flat on the page, the bond angles would be 60 degrees for cyclopropane, 90 degrees for cyclobutane, 108 degrees for cyclopentane, and 120 degrees for cyclohexane. Therefore, for planar ring systems, we would observe a significant angle strain, an unfavorable occurrence seen wherever there is deviation from an atom's ideal bond angles. Using only this information, you might expect cyclopentane to be the most energetically stable ring. This is due to the smallest amount of angle strain. However, in reality, cyclohexane has the lowest energy and is actually strain-free. So what's going on? Firstly, let's look at cyclopropane. There is limited flexibility in the ring, so the atoms lie flat on the plane. Looking at the ring from above, it's possible to observe that an ellipse conformation exists. This introduces torsional strain, which, combined with an angle strain of 49.5 degrees, makes cyclopropane relatively unfavorable. It is also worth pointing out that due to the 60-degree bond angle within cyclopropane, sp3 hybrid orbitals, which sit at angles of 109.5 degrees, have a poor end-on sigma overlap. This makes the bonds within cyclopropane weaker and therefore easier to break compared to the related straight chain propane. In planar cyclobutane, in addition to the angle strain of 19.5, you would also expect torsional strain to come from the ellipse conformation. However, with 4 carbon atoms in the ring this time, we have some more flexibility. The ring can pucker to produce a conformation with reduced angle and torsional strain, resulting in a slightly lower energy conformation. The same thought process can be applied to cyclopentane. Planar cyclopentane, with an angle strain of 1.5 degrees and an ellipse conformation, can be puckered to produce an envelope-like structure with reduced angle and torsional strain. But cyclohexane has the most impressive strain reduction and is in fact completely strain-free in reality. The cyclohexane ring puckers to produce a chair-like structure. When we look at this conformation side-on, we can see that the carbon atoms have the ideal 109.5 degree bond angles. By drawing a Newman projection, like this, we observe the chair structure has a completely staggered conformation. Therefore, since cyclohexane is free from both torsional and angle strain, it is the lowest energy ring system within the series of 3 to 6 membered rings. Drawing this chair structure on paper is a crucial skill for all 1601 students to master, so let's take a look at that now. Start with a point, draw 2 parallel lines down, and then add in the final lines to obtain the cyclohexane structure. Add the axial hydrogen atoms pointing vertically up and down, then finally add the equatorial hydrogen atoms which point outwards. The completed structure should look like this. Try practicing this a few times for yourself. Remember, it's not an art competition, but the drawing should be legible and clear to any examiner. Another point to recognize regarding cyclohexane is its ability to undergo ring flips. This involves axial substituents becoming equatorial, and equatorial substituents becoming axial. For example, in this cyclohexane chair structure, if we have an axial hydrogen labelled HA and an equatorial hydrogen labelled HB, a ring flip produces a structure where HB is now axial and HA is now equatorial. Note, the equilibrium arrow between the two structures represents the fact that ring flipping is a reversible process. Ring flipping becomes particularly important when larger substituents are attached to the cyclohexane ring. For example, we can add a methyl group to the ring. If this is in an axial position, there will be unfavorable 1,3 diaxial interactions with other axial groups located 3 carbons away. It is far more favorable for the methyl group to be sitting in an equatorial position where it has more space and less steric interactions. When we look at the Newman projection on paper, where the methyl group is axial, the substituent is gauche at 60 degrees to these two highlighted carbon-carbon bonds. After a ring flip, the methyl group moves to an equatorial position. The Newman projection indicates that the methyl group is anti-periplanar 180 degrees to these two carbon-carbon bonds. This becomes important during a later part of the CH1601 course. Try the quiz now to test your understanding of ring systems and cyclohexane ring flips.